Computing is a method by which we automate processing and transformation of information. Human beings have evolved to a level that they can develop tools to complete the tasks efficiently with minimal effort, be it pointed stones, spears, hammers, knives, calculators, computers, to robots. They're all merely tools invented by humans to reduce their workload and automate certain parts of their tasks which is otherwise tedious to do manually. Computers are also tools developed by humans to automate certain difficult and abstract tasks which is otherwise tedious to do. Quantum computers are a class of computers that use quantum mechanical phenomena like superposition and entanglement to perform computing. They can solve certain types of problems better than traditional computers. Traditional computers, which we use today, use electrical voltages to store and process information. This is done by interpreting high and low voltages as binary digits or bits. Quantum computers use quantum mechanical properties like spin of an electron or polarization of light to store and process information known as qubits. We will see more about bits and qubits in a later video. One of the main areas where quantum computers have an edge over traditional computers is parallelism. To understand parallelism, we will see an analogy. Let's say you have a set of balls of three different colors, say red, green, and blue, in a brown box and three different boxes of colors red, green, and blue. Our task at hand is to sort the balls in the brown box and place them in the box corresponding to its color. What will we as a human being do if we have to finish this task manually? We pick a ball from the brown box, examine its colors, and place it in the corresponding box. Generally, we do it one ball at a time and we pick up the next ball after we are done with the previous ball. This is called sequential execution of tasks. That is, subtask defined by placing one ball into one box is executed sequentially one after the other. This is exactly what a traditional computer does too. If you give it the instructions, say, pick up the ball from the brown box, examine the color of the ball, place it in the corresponding colored box. It will do it one after the other, albeit a little or a lot faster than human beings. Can we do it more efficiently and quickly? Of course we can, but the maximum a human can do is pick up two balls on each hand, examine both of them at the same time, and place them in their corresponding boxes. But can you pick up all the balls at once, examine them all at once, and place it into their corresponding boxes at the same time? Absolutely not. Perhaps if you had as many hands as the number of balls in the brown box? But what is the limit to it? Can you still do it if there are 100 balls in the box? 1,000? Impossible, isn't it? Theoretically, such a process is called parallel execution, where you could check all possible options at once and make a decision based on that simultaneously. Traditional computers also cannot do true parallel processing. True parallelism can be accomplished using a quantum computer. In order to understand the power of parallelism from a computing standpoint, let us look at a concept in computer science called algorithmic complexity. In simple terms, algorithmic complexity tells us what is the time taken to complete a certain task given the size of the input. In our case, the input is the balls that we are providing for the task. Let us say that we are taking one time unit to complete each subtask, picking up a ball, examining it, putting it in the corresponding box. So totally, it takes 3 time units to categorize one ball. Logically, for our task, it takes 30 time units to categorize 10 balls, 300 time units to categorize 100 balls, and so on. If n is the number of balls that we have, it takes us 3n time units to complete it. Now, this time unit depends on who is performing the task. If a small child is performing, the child might take 5 seconds per task, which correspondingly takes 3 into 5 into 10, which is 150 seconds for 10 balls, and 3 into 5 into 100, which is 1500 seconds for 100 balls, and so on. An adult might take 1 seconds for each task, and so 3 into 1 into 10 is equal to 30 seconds for 10 balls, and 3 into 1 into 100, which is 300 seconds for 100 balls correspondingly. A computer might take 0.1 second for each task, and so 3 into 0.1 into 10, which is 3 seconds for 10 balls, and 3 into 0.1 into 100, which is 30 seconds for 100 balls correspondingly. But regardless of who is performing the task, the time taken to complete it varies linearly over the number of inputs provided. In algorithmic complexity, such a linear task is said to have order n or O of n time complexity. Now, How many time units do you think it will take theoretically if we can do this task parallelly as we saw before? 3 time units, since it takes 1 time unit to take a look at the ball simultaneously, 1 time unit to examine the color of all the balls at once, and 1 time unit to place all the balls into its corresponding boxes. Again, done simultaneously. Regardless of how many balls are present in the brown box, it only takes 3 time units to complete the entire task. So, the time taken to complete it varies constantly over time, and in computer science, this is shown by the notation O of 1. So based on the notation that we have looked above, we can say that the parallel execution takes an order of 1 or O of 1 time for this task. This is the kind of speed up that quantum computer is capable of giving on certain problems. What kind of problems can quantum computing solve? Quantum computing can solve any kind of problem that a traditional computer can solve, only that for some problems it gives a speed up as a result of parallelism. For a quantum computer to be able to solve a certain problem, there should be a way to solve it in a traditional computer, be it in exponential time complexity. Although this is the case, applications of quantum computers can be staggering in our current situation of computing. For example, quantum computers can efficiently solve the problem of prime factorization. Since traditional computers take exponential time to factorize numbers, it is used in modern cryptography to encrypt messages in the internet. A quantum computer can factorize numbers in exponentially shorter time, breaking the current crypto systems. Whether the traditional computer can solve a problem as efficiently as a quantum computer is still an open question in computer science. This is related to the infamous P is equal to NP problem. What kind of problems quantum computers cannot solve? Quantum computers cannot solve any kind of problem that a traditional computer cannot solve. Alan Turing and Alonzo Church are famous mathematicians and computer scientists who set limitations of the kind of problems a traditional computers can solve. One example of a problem that a traditional computer cannot solve is the halting problem. In halting problem, our computer is given an algorithm that solves some other problem, and our computer's job is to answer the following question. If we run this algorithm on any computer, will it ever stop after a certain time? It can be proved mathematically that it can't be decided. Another example of undecidable problem is Hilbert's Entscheidungsproblem problem. In this series of videos, we are going to take a look at some introductory concepts of quantum computers. We are going to see the logical components of quantum computer like qubits and quantum circuits, what is possible to do and is not possible to do with quantum computers, quantum algorithms, simulation of quantum computing concepts using simulators like Qiskit or Microsoft Q Sharp. Okay, let's embark upon this beautiful journey